Okay, the welcome speech, I have to talk about the history of the indium galvanite-based LEDs. So you can see. There's a point. I don't know. It doesn't work. Okay. Okay. So basically, this is a red LEDs. So in the case of blue and green LEDs, so using nitride, for first nitride-based LED reported by Maroska in 1973. In this case, no p-type layer, so they developed MIS, metal insulator semiconductor LEDs, but very dim. And also, so in '89, Professor Akasaki and Amano developed the first gallium nitride PN junction LED. But when the active layers gallium nitride very dim, almost out of the range, almost zero. And so in our case, we developed the first indium-based LED, indium gallium nitride-based LED. It's so bright. Initially, we developed the conventional double heterostructure LEDs. Also, we changed the quantum LED structure in '95. So it's very, you can say, very bright, no? So indium gallium nitride has a totally different from gallium nitride. And this is our first report of the gallium nitride PN junction LEDs by Professor Akasaki and Amano in '89. And they reported this first LEDs, but very dim, so they couldn't measure the out power, also water efficiency, no data. Only they observed the electroluminescence of a violet. But this is first report. And also, our group in '91, also we made a gallium nitride PN home junction LEDs. And we measure out power, but very dim. Only out power is 40 microwatt. And water efficiency is 0.18%. Very dim. When gallium nitride is actively very, very dim. So we are so disappointed. But in order to, so we expected, so we thought we had to make a double heterostructure LEDs. So in this case, double structure should be very bright because carrier density is very high, using confined carrier, in the small active region, no? So in that case, we need indium gallium nitride active layer. But the problem is in '90s, nobody could make indium gallium nitride materials. So several groups tried to grow indium gallium nitride. So materials, very poor materials. So this is our best material at that time. So from who? Matsuoka, Professor Matsuoka group reported a very good material. Best material, this one. At room temperature PR, this is a band edge emission. We can observe the band edge emission, but the low this is low, but room temperature. This is liquid nitrogen temperature. But room temperature, no band edge emission, only deep level emission. This is the best material, no? So nobody could use this material for the LEDs because room temperature, no band edge emission, only deep level emission. So that, but in our group, in '92, we could make the very good indium gallium material for the first time. At room temperature, we observed beautiful band edge emission, blue and violet. So because we have a special MOCVD system, so this is the first report. So we became very confident. Now we can use this material for the active layer to make LED, laser diode, everything. So we immediately made the LEDs, So, but initially we use for active layer, we use very thick indium gallium nitride active layer. Active layer is thickness like this. It's amazing thickness, 100 nanometer, 500 nanometer, more than critical thickness, But we didn't know that, at that time, critical thickness thing. But and we made the very bright LEDs. Output is 1.5 milliwatts. At 1.5 milliwatts, and the EQE external content 2.7%. And also in '95, we demonstrated the first quantum wire structure LEDs. This is using quantum wire active layer, we can make very bright blue, green, and yellow LEDs. And that power is almost 3 times higher than the conventional double structure LEDs. It's very bright. It's amazing, you know. So indium gallium nitride it's a totally different material in comparison to gallium nitride. It's very bright. Also PL measurement, PL intensity is very strong. Also, this is our first LEDs. You can see I intentionally use the aluminum gallium electron blocking layer. We didn't know the real load of this layer, but we needed this layer to increase the very bright LEDs. At that time, we didn't know the physics, you know. So also interesting is that in '95, Hewlett-Packard group in some, published this paper. This paper. They say, they analyze our LED, Nietzsche's our LEDs, and they reported this paper, and they said, our LED has a huge number of dislocated densities, more than 10 to the 10th, but still efficient. They said, why so efficient in spite of a huge number of dislocation? Because at Nietzsche, our company, small company, we never measured the dislocation at all. So we had no idea of dislocation. They said, so all of conventional 3-5 materials, if dislocation becomes more than 10 to the 6, no emission. But in the case of indium gallium nitride, 10 to the 10th is this out of range, still efficiency is very high. So that's the reason why so efficient, They also, so also we saw this paper, we are so surprised. We never measured dislocated density, so wow, And so another design. So, basically, so we plotted the Hewlett-Packard result. And so when you use the gallium nitride active layer, trend is very similar to conventional 3-5 materials. Still, nobody could use gallium nitride for active layer, for LED laser diode. When still we use a gallium nitride active layer for LED laser, very dim, no emission due to huge number of dislocation. Only indium gallium nitride. Indium nitride is, even for this is depends on the current density. When the current density is small, efficiency is still very high. But the increase of current density gradually decrease. But still very high efficiency in comparison to conventional 3-5 materials. So indium gallium is totally different materials. So the reason is in '96, Professor Chichibu reported that this is due to the localized states, which is caused by the alloy fluctuation of ternary compound. This is Professor Chichibu's idea. So he said, indium gallium nitride are ternary compound. So they are alloy fluctuation. So alloy fluctuation forms the localized states. So injected carriers easily capture these localized states before captured by the non-radicum center. So that is his idea. So in '96. And this is latest UCSB's measurement. So at UCSB, we use the atom probe tomography. Using this one, we observe the beautiful, random alloy fluctuation like this. So red region and the indium rich region. So this is a conduction bands and also valence band similar. Indium rich region has a narrow band gap, and indium poor region has a wide band gap. So basically, injected carriers easily captures these localized states. So that is their explanation, but still we don't know exact reason. So basically, you have a mathematician and theoretical physics people here, so you can exactly determine the reason why indium gallium nitride is so efficient. Because it's very interesting. Still, we cannot use gallium nitride for active layer. Nobody uses gallium nitride active layer for LED laser diode, even to make 360 nanometer UV LEDs. UV LED, still we use a small amount of indium into gallium nitride. So indium is very, very important. So also recently, indium nitride, we can make 1.5 micron. We observe 1.5 micron PL measurement recently. So using indium nitride, we can make a 1.5 micron emitting device to 360 nanometer. Also using aluminum gallium nitride activator, we can make 250 nanometer LEDs. So we can make, using 3.5, we can make 1.5 micron to 250 nanometer LEDs. So it means we don't need conventional 3.5 material anymore near future for emitting devices. So it's amazing. Okay, that's it. Thanks so much.